Thank you very much. Thank you also to the organizers, Dima, Christian. I always love to be back at IPAM, so I'm trying to behave nicely so that you invite me again. I'm supposed to kick this workshop off, and I think with this overall theme of electrochemical systems and bridging scales, I mean, this is a huge field, and so I should try to position what I'm going to talk about in this overall big field first to really get the right kind of stage. So I'm a catalysis person in this regards here, particularly electrocatalysis. And because electrocatalysis is all about surface reactions and getting this reactive chemistry, the kind of like natural scale where I come from is kind of like the atomistic or even the electronic scale, because so like we need a quantum mechanical kind of description to get the right account of the chemical bond making and breaking that is the heart and soul of electrocatalysis. And so this is the sort of like the natural scale for me, and that's in itself already a huge problem, a multi-scale problem. And in thermal catalysis, so like we're struggling with this for many, many decades already. Now, electrocatalysis from this perspective adds simply just additional complexities. And that is primarily, of course, the electric double layer that forms upon electrification of the solid-liquid interface. And of course, a liquid electrolyte is much more difficult to describe than just a gas phase surrounding that we would have in thermal catalysis. And primarily, we are facing a length scale problem, because the time scale problems is the same as in thermal catalysis. But in the length scale problem is basically that we have to describe sort of like this diffuse double layer that really extends over quite some dimensions that sort of like, if you come from that sort of like perspective of atomistic surface reactions, is way too large for us to describe. So one way or another, we have to coarse grain. What we do is we sometimes coarse grain electronic degrees of freedom, we coarse grain atomistic degrees of freedom, and sooner or later we also arrive then at continuum descriptions. And that's sort of like roughly the ballpark that our work is centered in, and what I would like to survey a little bit today. Basically, I'd like to talk about three different things. The simplest, where you directly bridge to continuum, of course, is to get rid of that stupid electrolyte and all of its atomistic complexity, so you make it a continuum, and that's implicit solvation. And there are ways to sort of like think about it that in particular introduce capacitive charging. That's what I would like to discuss first. Obviously, treating an electrolyte as a pure continuum is a very, very brutal approximation. And so we have to become better, or we have to at least have reference calculations that are fully explicit in the electrolyte. But then sort of like ab initio MD, that would be the standard way to do it, is of course super expensive. So machine learning here could be a new gateway. That's what I would like to discuss in the second part of the talk. And then eventually, it's not only about the electric double layer, but of course they're even larger scale, and I fully acknowledge this. I think we'll have talks in this week about much, much, much larger scales. The minimum that one has to think about is mesoscale transport phenomena in the electrolyte, because sort of like if you come from the perspective again of thermal catalysis, a reaction product that has desorbed is basically gone. That's not necessarily the case if you have a liquid all around you, because of course the transport processes in the electrolyte are much more complicated, and therefore, for example, chances for the product to reabsorb onto your surface, which is a negligible chance if you have a gas phase surrounding, but it's definitely something to worry about if you have a liquid. That would be the last part. And since we will allow questions, and I know the format of IPAM and I love it, can you please give me sometimes a 10-minute warning or so, because then I can see how I wrap it up if I really ever go through all of these. Great, thank you. Okay, first part. Coming back to this size problem, just to make it very, very simple, I mean, if this is kind of like an artistic rendering of maybe what a solid liquid interface and electrified interface looks like, that's our DFT supercell. So if we want to do quantum mechanics and do electronic structure theory, that's sort of like what we can capture. That's not the whole thing. And so you have to somehow do something to get the rest of the system into the game. And the simplest that one can always try to do is to use thermodynamic approaches. You basically switch to a grand canonical kind of picture, and you treat all of the rest that does not fit into that supercell as some sort of like a reservoir. And that's the heart and soul of approaches that are probably, as a common denominator, can be called ab initio thermodynamics approaches. In catalysis, they are super long established in thermal catalysis. So here, basically the reservoirs that one would take would be the gas phase species, typically reactants. And then you basically do your standard DFT kind of like calculations in your periodic boundary supercells. Oh, and I should mention that we have to do this because, of course, these are metallic electrodes. And if you want to describe the metallic electronic structure in the proper way, this has to be at least laterally periodic in this direction, and then most DFT codes are also written in a way that you want to have a periodic boundary conditions in this kind of direction. So here, sort of like we're treating then doing the standard DFT calculations, and we've set up thermodynamic equations with these different reservoirs where changes in the reaction conditions, so like changes in pressure and temperature in thermal catalysis, are reflected in the chemical potentials of these species that can enter or leave this kind of cell. That's great. In principle, you should be able to straightforwardly extend this kind of thinking to electrocatalysis. The problem in electrocatalysis, though, is that these are not just atomic species, but of course in the electrolyte, we have ions and we have electrons separately. And if you allow sort of like electrons and ions to be canonically entering or leaving your kind of surface, in the end, there are also system states where the overall charge in your periodic boundary supercell is not zero, because not necessarily do electrons and ions have to compensate each other. Just over breakfast, Axel and I had, of course, a heated discussion. We're roomies, as typically when we are at IPAM, and we always love to hate each other about these discussions. And he immediately said, no, it doesn't need to be charged. Well, of course, the overall electrified system is charge neutral in a sense, but we're describing a small subpart of that, and that, unfortunately, can very well be charged. So how do we go about this? Well, the standard equations that you would set up in initio thermodynamics would be stuff like this. You evaluate some surface free energies or other kinds of free energies. And normally in thermal catalysis, you would only have the reservoirs represented by these chemical potentials. Now you have to split this into ions and electronic chemical potentials. And this in principle would need to be charged. And that's a bummer because, of course, having a periodic boundary condition supercell with a finite charge is an electrostatic catastrophe. The DFT codes are resilient enough to basically go about it without saying something. They just renormalize everything because they introduce a homogeneous background charge to avoid that electrostatic catastrophe. So how can you go about it? The simplest way that you can do is you basically ignore that problem. And you say, well, I'm not allowing any charge states that are Q non-equal to zero. And that approach is called computational hydrogen electrode. For fairness reasons, one has to say that the authors of this, and this is Jens, of course, and Jan Rosmeisel, they came from a completely different perspective when they introduced this. Because a big problem, of course, when you want to solve these kind of equations is that you have these sort of like two separate reservoirs. And getting a solvated electron and the chemical potential of ions, that's tough from first principles. But if you basically do the two things together, that's the definition of the reversible hydrogen electrode. And so if you basically have charge equal to zero, then this means that these compensate each other and you have only just multiples of this, and then you don't have this referencing kind of problem. And that's why also this technique is called computational hydrogen electrode. And so this is very cool to solve the problem of your referencing around here, but as a implication of this, of course, means that you have only charge Q equals zero. And that means, of course, that in principle, you don't have any polarization of your surface. It's a very crude kind of way to do these or go into this problem because you do have the effect of the electrification in the form of the external reservoirs that enter into this equation. But at the electronic structure level, your surface doesn't see any effect of an applied bias. It remains at the potential of zero charge. There is no charging in there. So it's kind of like a hybrid. It allows to capture already sort of like some first order kind of effects, but it does make a lot of things not right. And in particular, what is most important is, of course, that if you have an electrification of your metallic electrode, you will have charge compensation or counter charges in the electrolyte that will come close to the surface, and you build up an electric field and you have a capacitive charging. And you don't have that at all in the computational hydrogen electrode by construction. Now, how can you go about it? Initially, people, first of all, also thought about let's do implicit solvation. So let's treat the electrolyte as a continuum. I think, again, the original idea was simply, okay, you can do the computational hydrogen electrode and not even have any solvent model or so at all. You basically do these calculations in vacuum. Since you're not actually charging your surface in the electronic structure calculation, the effect of a solvent is very, very small anyways, and so let's forget about it. And so then people said, okay, maybe we should at least consider it, and the simplest approach is implicit solvation. You treat your solvent as a continuum. I wanted to mention Richard, but he's not here because he has to give a lecture, and so I'm not mentioning him. But of course, Richard with VASP-SOL would be one of these guys who majorly drove this with introducing VASP-SOL or so. And whenever you have some functionality in a DFT code that doesn't cost anything and you don't need to think about it, then it will immediately appear in about 500 publications. And so this became very popular, and there's now zillions of ways of doing implicit solvation models, and maybe we're hearing more about it in this week. For me, they're just a very, very simple way to introduce the countercharges, because what you can then do is, if you have an implicit solvent model, is that you basically can charge your surface, so you do Q non-equal 0, but so you put more electrons or less electrons into your electronic structure calculation, but you compensate this with a corresponding countercharge in the implicit solvent. And because you have it somehow embedded in the high dielectric, because we're typically doing aqueous electrolytes, that means the exact position of these countercharges, so it also doesn't really matter because that's screened anyways. Overall, it just ensures that we're charge neutral, and we can do the periodic boundary calculation. And so this approach now, because now you're doing sort of like the grand canonical thing here, not coupled, these two reservoirs, but independent of each other. Nico Hermann, who is the main driver of this in my group, called these things fully grand canonical. They're still not, it's not true, because it's not really fully grand canonical, because we're actually not doing fully grand canonical in the sense that actually into the actual simulation, ions or species could go, leave or enter. That we don't do this. We do many, many different calculations at different stoichiometries, and then only use the thermodynamics later on to compare all these kind of calculations. Nevertheless, he called them FGC. And that it doesn't really cost much, because the implicit solvation doesn't cost much in the DFT kind of calculations, and you can suddenly now introduce Q equals 0, non-zero. So Nico was here in the first workshop. Those of you who already attended it might remember his talk. I don't want to repeat all of this. Anyways, if you suddenly do this, you can introduce the physics that you introduce with this is capacitive charging. That's it. Solvent is shit. It's really crude because it's an implicit solvent, but you get capacitive charging, and you get a couple of things in electrochemistry right. And the thing that I would like to discuss a little bit more in detail is, for example, that you get potentially dependent adsorption energies. That's a big thing, because, as I said, the standard approach that we had about 5 years ago in this field, coming from the first principle side, is computational hydrogen electrode, where you have basically no field effects on the electronic structure level. And people use this to compute many, many adsorption energies, because this is in our field in catalysis sort of like descriptors. Either you really try to set up microkinetic models, or you compute these descriptors to do materials discovery and say, okay, you found the next super cool catalyst kind of material. So adsorption energies are a big thing in our field. And if you take a neutral molecule like CO, which of course is a very important reaction intermediate, for example, in CO2 reduction, and you compute in the CHE, its adsorption energy, as a function of the applied bias. You can do that, of course, in the grand canonical reservoir by in the CHE approach. The adsorption energy is, of course, constant, doesn't change. Why would it? There's no charge leaving or entering, it's always the same. Whereas if you do this in this fully grand canonical kind of approach, et voila, your adsorption energy changes actually by quite a bit. And that's simply capacitive charging, because what you're actually having is so-called dipole field effects. If you go into this direction, for example, your electrolyte, sort of like you would have this sort of like a charging of the surface like this, and your electrolyte overall would be charged in this direction. And of course, a molecule like CO is not charged, but it has a dipole moment. And that dipole moment now in this direction is sort of like aligned in a way that overall these two things don't like each other, and you get a weaker binding. On the other hand, if you go in this charge direction, it's sort of like in the right kind of direction, and you increase the binding. And even so, like if you do back of the envelope kind of thinking, you see really that these changes that we get out of DFT with loads of CPU hours is basically something that you can do in a one-liner, because it's just sort of like, by dipole field, you would think, okay, this is the molecular dipole moment of molecular CO. This is roughly what we do, volt per angstrom. That's the field roughly that you will build up. And overall, you see exactly we get these kind of variations. Cool. That's super important because that's not a minor effect. Huh? So we are changing the adsorption energy about 0.1 electron volt or so in a reasonable voltage range. If you think of this as being a super cool descriptor for telling you that this is a good catalyst material or not, this makes a difference. And in the CHE, this is not accounted for. Immediately, the physicist in me went wild and said, okay, if we can get potential-dependent adsorption energies, how about protrusions at the electrode? Because typically, of course, we think of a planar model electrode or so, but atomistically, even a planar model electrode that you have in experiments is not planar. It has protrusions. Simplest would be step and kink atoms that you would have at the lowest scale. Now, if we charge this, these protrusions stick out, and you will have an increase of your local field effect because that's where the charge will go dramatically. And so the question was, if this is the variations of these adsorption energies are basically a dipole field kind of thing, if I have active sites at the surface, or sites where my molecules can bind to, where there should be a much, much, much larger local electric field, I should have even larger variations of the adsorption energies, and that could, change the role of these sites with changing potential dramatically. They are already special anyways because these are typically under-coordinated sites, so the chemistry is different, but that would be on top of it that you would actually get an effect because of the dipole field effects. So we wanted to look at this, and by simply going into simple model vicinal surfaces which exhibit steps and kinks, and we did these kind of two vicinal single crystal surfaces because they basically have the same steps and the same kinks, just in different kinds of spacings. And because we also wanted to see how local this is. And what you already see here in the color code is actually a charging of the surface sites with respect to sort of like the normal state. So our delta Q of 1 normalized means this is basically the charge that you would have on the atom in a terrace. And you see, of course, exactly as what we expect. If you apply a bias, sort of like you have most charge actually on the most protruding kink sites and a little bit more on the step sites. So you would think, okay, I've understood all of this. Let's do the calculation. So adsorption, the adsorption energy should vary much, much, much more for a molecule adsorbed at these kink sites than intermediate here, and then the weakest at the terrace. Never believe that you have understood something, because if you do the actual calculations, it's the exact opposite. So you have what I showed you before here, the variation on the terrace, but at the edge and kink, in particular the kink, there's essentially no variation left. Apparently we haven't understood something. Well, it's simply the reasoning is that you think, okay, I have my surface charging and then I put a molecule and nothing happens, is too simple. The molecule chemisorbs to the surface, and this way it becomes part of the metallic electron density, so to speak. And of course now, if you put a CO molecule as a probe, for example, on a kink site, this is the new antenna that will stick out. That's the new protrusion. That's where all the charge will actually go. And so if you compute the accumulated charge, not for the clean surface, but with the adsorbate on top, you see that there's basically very little charging left on the kink site atom. Instead, all of it, this charge has actually gone onto the CO molecule here. And that, of course, then changes the dipole moment of this, because the dipole moment is not the molecular one, but it's the effective surface dipole moment that the molecule has in this adsorption geometry. And so if you make a very simple back of the envelope kind of calculation, you say, okay, well, if this charging sort of like has all gone into the adsorbates, and roughly I don't need to worry about this anymore, I can basically, again, think of this surface as a planar, sort of like a plane surface, and then simply do my plate capacitor type of field. And instead, now use the effective surface dipole moment, which I can access in the calculations by computing the work function and doing Helmholtz. Then I can sort of like effectively write the change of adsorption energy approximately in a perturbation theory with this as the leading order term. And if you do this, you see that all of our cool full canonical simulations can sort of like be very, very roughly reproduced by this very simple understanding. So it's basically really dipole field effects. It's just effective surface dipole, not the molecular dipole one, and it is the charge of the surface that it has in the adsorbed state. And that works very nicely. We did it for many probe molecules and many different kink and step sites, and you get sort of like always this very good relation, and you, again, repeating very large variations of the adsorption energies that now, with stuff that doesn't cost anything, in particular this approximate thing really doesn't cost you anything. You don't even need to do a charge calculation. You can still do your computational hydrogen electrode calculation and just do the analytical correction for it, and you would get potential dependent adsorption energies, and then you can do whatever you want with it without any extra computational costs. Good. Great, we can do capacitive charging. Good, I can go home, I can finally play golf for the rest of my life. Cool. No, because implicit solvation is, of course, very, very crude. So let's see, just highlight, because I'm quite sure that we will have many talks here that will highlight explicit solvation, some of the effects that one can expect. For this, let me change to a different reaction. So ORR on gold is always of interest because these weak binding electrodes are the ones that actually do not produce simply water, but hydrogen peroxide, which would be much more valuable. And it's kind of like a mystery why this actually forms, because if you only think of the thermochemistry, kind of like this is much more downhill, so everything should produce this. And it's sort of like always has been a long-standing mystery why some of the weak binding electrodes like gold produce hydrogen peroxide. In order to do that, you have to bring the oxygen onto the electrode in the first place. And gold is not a particularly reactive surface. So O2 is, and furthermore, O2 is a very hard molecule to break. So why would this actually want to undergo any binding at all? And so you see again the same story, potential-dependent adsorption energy. So this is the adsorption energy of oxygen that we compute against the surface charge density. This is how much we charge the surface. You can sort of like translate this roughly into a potential dependence. Now, the experimental ORR is roughly around here. You can go even one step cruder than implicit solvation. You just apply a sawtooth potential. Then you don't even have a dielectric continuum in your cell anymore. And you would, of course, sort of like get something as you expect. The more you charge your surface, suddenly you do get adsorption energy. And whereas in the potential of zero charge, gold would definitely not want to bind O2, so around here, basically it becomes negative. So only at around these potentials will the surface bind oxygen at all. And that is, of course, the first thing why you would actually get this as an onset potential, because if you can't bind your reactant onto the surface, you cannot do the reactions. Implicit solvation is then actually, as I said, it's very crude, only a very minor correction to it, because somehow, because of the dielectric, you do have some sort of like a bonding or a solvation effect in it, but it's actually very weak. You get roughly what you expect also from a simple sawtooth. Now, if you go basically from this does not cost anything to let's squeeze and torture the Max-Planck supercomputers for a while, you can do ab initio molecular dynamics, which is, of course, horrendously expensive to do that. Lang is already looking at me because she's a master in these kind of calculations, and she only counts CPU hours in the millions. And of course, if you do explicit simulation, I don't want to go into this today, you have all your own problems with the countercharging, and I think Lang has already, or Nico has talked about it in his talk, and Lang has a poster on this. But let's say we can do it. And of course, even though this is shitty expensive, there's a lot of noise in there because we can't do this for long enough, these simulations. But what you get out of it is roughly you see, the crude models capture the right kind of effect apart from around here. So here suddenly something new is kicking in. And it's very simple to explain. It's because around in this new regime, you get a completely different adsorption configuration. The molecule goes much closer to the surface. And what is happening is actually that if you look at the number of hydrogen bonds that the adsorbate is actually coordinated to, suddenly around here it goes from 2 to 4. And that's already an obvious crude limitation of implicit solvation. You have no hydrogen bonding. You can't, because it's a continuum. And around here, you basically charge your oxygen molecule so much that it would like to change its oxidation state. You can see this if you evaluate it, so the lighter the color, the less charging, so this is more and more applied negative potential, and you see reflected in the distance as well as on the charge that what we basically do, we go from a superoxo state to a peroxide-like kind of state, simply because there's more hydrogen coordinating to the oxygen molecule. And that makes this kink, and that's of course something that you cannot get in an implicit solvation model because we don't have any hydrogen bond or directed hydrogen bonds in this continuum description. Apart from the fluctuations, there's of course a big theme here, the fluctuation. Of course, you don't have any fluctuations in implicit solvation. So it's nice, efficient, very easy, but it's very crude. So let's try to think how can we do explicit better because of these obvious limitations of implicit solvation. But then let's not do ab initio molecular dynamics because that's a killer. Second chapter. machine learning. Solution 42 these days, everything where you have a problem that you think is unsolvable, you somehow throw machine learning into it and it suddenly works. So here, the solution that machine learning offers are so-called machine-learned force fields or machine-learned interatomic potentials, MLIPs, and they are all over. In particular, now that we have arrived at the production stage of these things with these so-called foundational machine-learned force fields that are trained on huge databases and are more or less production ready for essentially the entire periodic system, you typically need to fine-tune them a little bit to the specific system that you do, but that's very little work, and then you can more or less use them out of the box. And I don't want to go into the technical details. I'm also quite sure that we will have talks on this during this week. They basically evaluate the local atomics environment and then sort of like compare this, how similar is this to environments that I have in the database. That's the only thing, it's a surrogate model that these things do. The important thing to think when you try to think how can I use these for electrified solid-liquid interfaces is that this evaluation of the similarity of the local atomic environment is always local. They do it up to a certain cutoff. And that the smaller the cutoff, the more efficient the force field, of course. And so anything that's a long-range effect, like long-range electrostatics, which you would expect, of course, think of a electric double layer. That's long-range electrostatics galore. So that's very difficult to get in this local description. And just to show you how bad this is, let me do a small detour very quickly through batteries, which we're also working on, where you have the same kind of problems. And we just had this nice tutorial example there. In batteries, it's not about the reactive chemistry, it's about ion mobilities, of course, lithium ion mobilities. And the nice thing with these force fields is if you take a complicated battery material, a solid-state electrolyte like LPS, you can not only do the ionic mobility simulations, which of course very large dynamical simulations, for the ordered crystal phases, but you can also do them for larger disordered phases. And this is at the moment discussed as a key property in solid-state electrolytes to really form these amorphous states close to the grain boundaries in them. Now, cool that you can do it, but again, it's the same problem as in electrocatalysis. A battery material doesn't live in free space. It lives inside a device. And if you set up a device, you will have fields. And in a battery, so if you make a large-scale continuum battery model, of course you see that the big fields, or the drop-off of your potential, occur very close to the cathodes and anodes. And a very simple descriptor, because one of the big problems with these solid-state electrolytes is that they're unstable eventually under operation conditions. And a very crude way to assess this is to basically compute the cost of creating a vacancy, a point defect in them. Because if that formation energy for a vacancy becomes, in a sense, favorable, so that you can gain energy by creating a vacancy, that's bulk thermodynamics telling you that this material is unstable. And so we thought, okay, let's do the machine-learned force field now that we can do it, and here's my defect formation energy as a function of an applied field that I would expect here, and let's see what it gives. Nothing, because the machine-learned force field is blind to the field. It doesn't see it. It's long-range electrostatics, which it doesn't have because it's only evaluating the local similarity of the local atomic environment. If you do the latest generation of force fields with message passing, with every step of message passing, you can go a little bit further out. But basically, you also make your machine-learned force field so much smaller that at the maximum at the moment, what they do is one message passing step. So it's still, maybe in the DFT language, we would call it semi-local. Not long range at all. So of course, what is missing is the long range electrostatics. Super crudely, zeroth order, what you can simply do is you can put electrostatic point charges on all of your atoms, formal point charges that you have, and then basically evaluate the Coulomb sum. Great, because something that one should never forget in machine learning is that there's about 200 years of physics and chemistry. We have understood a couple of things. I mean, the computing science people typically tell us to forget all of this because apparently you can all learn it from data. But as a physicist, I strongly object to this. Everything that we have understood, we should probably also use, and then we can do the data, do the rest. Anyway, so we do understand this, and if we put the super crude model then in, and so we augment the short-range machine-learned force field with a long-range description of electrostatics, a simple point charge model with formal charges. Of course, the defect formation energies do what they should do. They depend on the field, and eventually they become negative. In particular, you also see that this is anisotropic. the material is anisotropic, so it will depend on the relative orientation of your grain with respect to the electrode, and that's actually what they see in experiment. Cool, but that's super qualitative. So how can we do better? At the moment, this entire field goes for coupling it to better long-range physical models. In one way or the other, they're all based on charge equilibration. That's old Andy Rapp, when he was still with Bill Goddard, a long time ago. It's a very nice but very simple model. So it's basically, so you have your short-range energetics and you augment it with a long-range term, which is your standard Coulomb. And here you basically have electronegativities and the hardness in there, sort of like to account for polarization and charge transfer kind of effects. And you try to find that sort of like arrangement of charges that minimizes that energy, so that it's equilibrated. That's why it's called charge equilibration. Now, so far so cool. We also have our local version of it. We call it kernel charge equilibration because we originally did it for the kernel machine and force fields. If you now take a couple of water molecules and you basically evaluate them under an applied field, they're charging the Hirschfeld charges. What you see is, of course, this is exactly in DFT. DFT does it right. You get a polarization of your molecule. Of course, the charge goes in the direction of the field. Whereas if you do it with the charge equilibration, it overpolarizes. What you actually get is not a polarization of every individual molecule, but because you do the minimization of the sum globally, it basically thinks that your system is metallic, and it can rearrange the charges in everything. And so what it does, it charges up some of the water molecules entirely in the one direction and entirely in the other kind of direction. That is actually known. So charge equilibration is from the 90s. So many people in classical force fields use charge equilibration for long-range electrostatics, and it's known that you overpolarize it. It's just that the machine learning community is basically built from people that do not read papers that predate 2015, because then, that's not machine learning, so it's uncool. And so you get basically out what we just rediscovered, and see, because it's machine learning, you can even publish it in Nature CompMath. We get out what these people already discovered 20 years ago. If you do these water molecules and now do an MD simulation, you get super cool physics out, because originally you have your cluster of water molecules, and then some walk in the direction of the field and some in the other, because you overpolarize. And it's complete nonsense. So basically what it says is that by construction, any long-range augmented machine learned force field that is currently out on the market that uses charge equilibration models will be absolutely unsuitable to do electrochemistry or electrocatalysis with it. Bummer. This is why we went for a completely different route. So those of you who have met Nico Hermann when he was here a couple of weeks ago, so Nico loves analytical theory, in particular perturbation theory, particular to second order. So that's what he does for a living. And so he basically thought, well, if we want to get an energy that depends on charge, why don't we write our typical expansion in second order in the charge? And then we see for these terms, and rather than trying to learn a charge-dependent energetics and try to build up a machine-learned force field that gets this charge-dependent energetics, we take basically a standard force field from the shelf, which is for the E0, and then we try to learn the response properties separately in it. And the nice thing is that it actually can follow exactly the same scheme, because what we do when we learn the total energy is that we do this decomposition into contributions from every atom, dependent on some descriptor that describes the local atomic environment. And we use the forces to stabilize this kind of learning, because then out of one training calculation you get a lot of input. You can do the same approach if you now say, okay, this first order term, that's the work function. Let's learn the work function and basically write it as a polarization, and then make the same approximation as the sum of individual polarizations that depend on the same local atomic descriptor. And in order to stabilize this, I do take again this first derivative, when this is the Born effective charges. Both of these are quantities that I get out of DFT calculations. Now, second order term, at the moment we do very crude things, because this is very new. So we basically, Nico has arguments that say this is sort of like not, varying too much, is roughly a constant. But we already see that this might be too crude. But at least the first order were kind of like good. This is second half order, I would say at the moment. Don't tell Nico. Nico, don't listen to this in YouTube. And then what you do is basically that you have a very simple way to do it. So you do your standard machine learned force field. And in order to learn this, what you need is now you basically take additional configurations from your interfacial system that you're interested in. You do calculations at a negative and slightly positive charge so that you get a numerical evaluation for your partial derivative. And that basically gives you, from this, you can learn the Born effective charges and the work function. And then you use all of this to put this back into this equation. And suddenly you have a machine learned force field energetics that depends or is sort of like has the long-range electrostatics into it, at least from second-order perturbation theory. Downside is only second-order perturbation theory. Upside, it is second-order perturbation theory. Because, machine learning is cool because of its expressiveness. It can fit you anything. But it can also, is super happy to fit you anything that's non-physical. Perturbation theory, if it's correct in the sense that the terms become smaller, basically take care that you're not getting complete nonsense in between this. You might truncate too early, and the terms that you don't have anymore are maybe important, but at least it's more robust and stable. And so we call this approach RAZOR, just published in PRL. And a very, very simple first way to show how it works is we looked at the adsorption side of hydroxyls on copper. So if you do the charging in the two different kinds of directions, because what you see, or the system is known for that, that's why we took it, is that you get a charge-dependent adsorption side switch. You see it here evaluated by the orientation of your hydroxyls on the surface. And you see here the results of machine learned force field MD simulations. Of course, you can many. Now we get the fluctuations. Good, important for this workshop in here. So we have fluctuations in there, but of course you get also an average. And you see the average angle, it really changes sort of like drastically, because what you see around this charging state here is that it switches from the bridge side with the hydroxyl sort of like mostly bent to the surface to one in the hollow side where it's upright. And you see it also reflected in the work function. And that's kind of like neat and important, because if you now convert this to a Legendre transform from the charging to the potential, and you plot this as a function of the potential with this RHE, you can see, evaluate your adsorption-free energy when sort of like the hydroxyls would go onto the surface, and you see that you need a certain potential to actually bring them onto the surface. And now it is different whether you do this in alkaline or in acidic conditions, because sort of like the time when this actually starts is different. And because you have this position dependence in this, it's sort of like in alkaline, you sort of like still, and this is the light blue, remain in this bridge kind of like position. And so you basically already allow the adsorption of this. The surface will become covered, but initially with OHs in a bridge position and only much higher potentials will it change to hollow. Whereas if you do the same in acidic, this change between bridge and hollow occurs already here when it's not stable at all on the surface yet. So when you finally get these things to stabilize on the surface, they will directly be in hollow. And that is seen in experiment. Depending on the acidity of your electrolyte, you basically either get initially bridge side adsorption or hollow side adsorption, and it is a consequence of this sort of like charge dependence of the adsorption side. And with these machine learned force field simulations, we get this. Admittedly, we would have also gotten it out of static calculations because that was known. But now we can do it with MD, and we have the fluctuations, and it was really only a first demonstration that in principle you can now do machine learned force field dynamical simulations. Do I have 10 more minutes? Yeah. 11, great. Should we do a coffee break? No, cool. So final thing, everything that I have discussed up to now is really coming from this. I'm a bottom-up guy, so I think active site, quantum mechanics, chemistry, and then I'm trying to become larger. And at least we try to somehow get the electrolyte effects into the game and the charging effects. But of course, there's a world beyond this to larger scales. And that's what I would like to discuss at the later stage, but now going to transport a little bit. And I would like to discuss this with one of the big fields at the moment in our in electrocatalysis, and that's of course CO2 reduction. Everybody's crazy for it. Obviously, we need to get it work anyways to survive on this planet. So it's not only fundamental science, but actually important. And it's not only CO2 or R, but any of these. properties. And so what people actually do is that they, so to speak, nanostructure electrocatalysts, because despite all of the glory of materials discovery and AI that we have, at the end of the day, the only material that they have found so far that actually produces something that's not CO in CO2 reduction, that's copper. Great job, huh? 10 years of materials discovery, copper. But at least what you can do is you can torture copper to death. You can basically synthesize it in all sorts of different ways. You can first oxidize it and then reduce it again, and many different forms of how you can torture copper. And the fun thing is, and you can try to alloy it, etc. Every time people see a different selectivity out of there. I have to be very careful what I'm saying because this is on YouTube. This will survive forever. It's a nice production recipe to produce high papers in glossy journals. You torture copper, you get a little bit of a different selectivity, you do some DFT calculations that somehow create a model for a new active site. You claim that this new active site is the key behind the observed different selectivities, and you publish. Let's leave it roughly at this. And eventually, you just ask yourself, how many active sites can I get out of copper, in a sense? And maybe there's something more or different physics actually to it. It might be that this is all right, but maybe there is more to it. And there is a nice world behind it, and that's mesoscopic mass transport, and this is this reabsorption that I directly mentioned at the beginning. Of course, I'm not the first person to think about it. There are always much more intelligent people than me thinking about stuff before me. In this case, it was Jürgen Behm. And he came up, and Axel knows him quite well, so Jürgen was in Ulm, of course, a huge electrochemistry guy. And he came up with the idea of this reabsorption mechanism. It goes like this. So it sums, of course, anywhere along an electrocatalytic reaction, you might actually have a reaction intermediate that in itself is a closed shell molecule and could therefore nicely desorb. In CO2 reduction, for example, the simplest first thing is that you reduce to CO. That thing, in principle, can desorb. And now you create a bifurcation, because either that thing desorbs, or it stays on the surface to be further reduced, and you have further catalytic steps, converting it into something else. And now, this gives rise to this model, which Jürgen coined desorption, diffusion, readsorption model, because if it desorbs, of course, there's also a certain probability, because of the liquid electrolyte surrounding, that it actually readsorbs. And so you have a competition between the surface chemistry, which goes along this route, and diffusion in here, so it's sensitive to transport. And what you basically can do is you can try to formalize this. Now, at least here's a little contribution from us theoreticians, by saying, okay, this route that you basically go further down the chemistry route, that's of course dependent on whatever is the next reaction barrier in here. And that barrier, that's potential dependent. If we increase our potential, we increase the driving force for this, and so we make that barrier lower, and it makes sort of like this way nicer. So again, so if you think of CO2 reduction as the other way around, so you make a more reducing potential, and basically what you would expect, if you make this path more favorable, and you measure the selectivity to this early product in here, this should go down, because there's less chances for things to desorb because you make this nicer. How can I make this nicer, or what is a descriptor for this in the reabsorption? And here is an important concept which is called the electrochemically active surface area. Imagine it as a density of active sites that you have sort of like on the surface. Because reabsorption, of course, that depends on this. The more active sites that I have, if my molecule re-impinges onto the surface and it doesn't find any free site, well, nothing will happen. If there's many active sites, a lot of this will happen. And this is roughly measured by this ECSA, which is simply, or the roughness, is the fraction of the true electrochemically active surface area, so how many active sites do I have, with respect to simply the geometric surface area. And so, the selectivity towards this early product, it basically should go down the rougher your surface is, because you have more and more active sites on there, and basically sort of like the reabsorption becomes more favorable, and then when it's reabsorbed, it can further go down this kind of like route. So you have very simple dependencies that you have in this, and this goes on different scales. So this could, the roughness is a very crude measure. Experimentalists can actually measure it. if they care to. They typically don't, but good experimentalists will report the roughness of their electrodes. And so this can be sort of like nanoparticle to mesoscopic roughness, but also the interparticle, the actual roughened surfaces or so. That all goes into the same descriptor, which they call roughness. It's a scalar. And so how can we now set up a model? As I said, we have first the simplest microkinetic model you can imagine, a mean field microkinetic model. Basically, it says the probability for these guys to be adsorbed on the surface depends, of course, on that barrier. What I need is the barrier for activation this way and this way around, and the electrochemical one and the desorption one. Okay, and the transfer coefficient, I don't care. A very simple, crude model. And then diffusion, which we take a very simple Fickian diffusion, 1D transport models, is super crude. This is modeling for the young people. There used to be something that is, you do not simply crank up a DFT calculation, but you take a piece of paper and you do a model. That means you make a very crude, simple thing that you can understand as a human. We don't do this these days anymore, but that was how we did physics, or no, even before my times. Anyways, so what do you do for such a simple 1D model? A couple of things. You can vary them up and down. It doesn't really matter much. It's not very influential on this. And then with this model, what you can do is you can simply go through the experimental literature, through all of these papers that have been published. And already the very first one, actually from Jürgen himself, he did a very nice approach in nanolithography, actually with Ben Casimo, he did these samples. So basically they could vary the roughness by this nanolithography. And they did not get CO2 reduction, but into this ORR, so peroxide formation. And peroxide is an early product, so again, the selectivity is exactly as you expect. The rougher you make your surface, which is sort of like with these different nanolith things, selectivity goes down. This is what our model predicts. It's a 1D transport model coupled to the crudest mean field microkinetic model with one reaction, the rate determining one that you can put in there. You have to, of course, fit it to something, so somewhere we fix it, but then anything relative in here is sort of like predicted by the model. Doesn't look too bad, but it's also super simple. So can we do more complex? Of course, you do CO2 reduction. And as I said, there are a couple of points where this actually produces these closed shell intermediates. CO is the first one, I discussed it already, but then you also have acetate and acetaldehyde later on down here in this reaction network. Now, I'll be very quick. This is a couple of, very nice journals, nice papers. What they again do is the selectivity versus the potential. It's all on copper. This is single crystal surfaces of copper. This is polycrystalline copper. You get these sort of like selectivity curves, and you get exactly what you would expect from the model as well, because you change the roughness, and our model predicts it. Again, we fit it to one of these points. All the rest comes out of the model, relatively speaking. There's no free fit parameter in itself. And now you do the tortured copper. So OD stands for oxygen-derived copper. This is when you first oxidize and reduce. And we're not everything is fixed from this here. We're not changing any parameter anymore in our model. And you just change the roughness. You predict this kind of data. It's all new active sites, according to literature. Simple 1D transport model gives it roughly the same. You can do the same thing now with acetaldehyde later on down the way. Again, same thing. It's not perfect, but you get the overall trends. You get it basically in terms of this reabsorption kind of thing. So, and then finally here, so here the curves are a little bit more complicated because this acetate undergoes a solutional reaction. This is a little bit more complicated. So what we predict from our model is roughly this, but again, it fits the experimental corridor. So suddenly you can basically discuss an entire bunch of experimental literature, all in the same simple model that you can write down on a piece of paper, and that has only a couple of free parameters. So, I know. Conclusion of this last part is basically that the mesoscale transport could be really as important as all of the surface chemistry that I predominantly discussed in the first part of my talk. This brings me, of course, out of my home turf. I'm more, atomistic kind of like guy, and I think this is why also this workshop is super, super critical. Also, definitely for my own work, I hope to learn a lot. Simply because if we go to these mesoscopic scales, we cannot do DFT anymore. This is no way. So we have to couple somehow to mesoscale transport. We have to incorporate the mesoscale roughness of our electrodes into the game. Directly going to Continuum might actually overshoot it. We can discuss that. But then anything in between could be really important. And I think this is why this workshop is really, I can only just applaud to the organizers. This is one of the crucial things that we have to find out. Because just doing implicit solvation and thinking that everything in the double layers doesn't matter, it doesn't cut it. Atomistically explicit simulations, maybe with a machine-learned force field, can help us a lot, but also that will not cut it. Eventually, we really need to account for everything, at least to the mesoscale, in some way, and we need to coarse grain. And I hope that we can achieve quite some progress in this workshop. Of course, I should not finish without thanking the people that actually do the work. So here I highlighted the individual PhDs and postdocs already on the slides, but the primary thanks should go to the group leaders in my department that were involved in here, and they should get all the credit. They are the really intelligent guys here. Money comes from this, and I thank you for your attention.